Okay, so this reaction, we're recording. This reaction is acid catalyzed hydration. That's the second reaction we'll be learning in our alkene series. All that happens, and I just want to go over a review of E1. Okay, E1, what happens is that you start off with some kind of alcohol. Okay, there is concentrated H2SO4, and there's no water. You protonate that OH. It leaves, forms a carbocation. There is no nucleophile present to do an SN1, so you do an E1 and you form a double bond. It doesn't necessarily have to always write heat. You can just write concentrated H2SO4 as well. If you have dilute, that means you have water. So you're protonating. This is the other way, going back to the alcohol. I'm going to grab the H of the H2SO4. The carbon with more H's gets the H. And the other carbon gets a positive charge. What happens is that water, in our previous video, is a weak base, poor nucleophile. We'll still react SN1 method to form an alcohol. And we'll form it at the more substituted carbon. Okay. So why is it that we can't use HCl or HI? Well, that would just be our previous reaction, right? So what we want to do, when I say previous reaction, I'm talking about the one from the previous video, which is, if you use HCl, then this wouldn't happen. You'd have hydrohalogenation, because Cl minus, last time I checked, is a stronger nucleophile than water. So that's why you have to use H2SO4 or that. And by the way, these are not nucleophilic. So these really fall in the category as water and alcohol. And these are actually stable. I know that a lot of people get confused. If this was even a CH3, this would also be stable. Because people think that I talked about electron density and let you know, if this was not an OH, but this is a side note, this was CH3, this is still very weak base. It's not nucleophilic, it's bulky. This negative charge, those electrons can resonate between all the oxygens. Okay, that's why. You need H2SO4 or H3PO4, right? To have this happen. Because if you use any of the salts or mineral acids, they just have their conjugate bases of nucleophilic and they'll just go attack the carbocation. The rule's still the same applied as Markov-Nikod's rule. The carbon with more H's gets the H. Simple as that. And the other carbon ends up being positively charged, right? So you do top or bottom. I drew the squiggly line because what we're adding in this case is water. Okay? So water can attack top or bottom. So if there's one chiral center that has changed, you form enantiomers or racemic mixture. Okay? There was another one out here. Let's say there's another chiral center out here. I'll just draw a random carbon chain. It doesn't change, it would be diastereomers. So again, in acid catalyzed hydration, you use H2SO4 or H3PO4. And then it's dilute, so water goes and substitutes into the carbocation. Which carbon gets the H's? The carbon with more H's gets the H, Markov-Nikod's rule. You form a carbocation as well in this reaction, so there could be a shift. So be careful. So that is acid catalyzed hydration.